You ever look at a piece of high-tech gear, like a turbine blade in a jet engine or a medical implant, and just marvel at how perfectly smooth it is? Well, it turns out getting that flawless finish isn't just about polishing. It's a full-on microscopic war against physics, where the very tool doing the creating is also trying to destroy its own work. So let's dive into the wild and, believe it or not, kind of violent world of getting a perfect surface.
So why the big deal? I mean, what's so important about being smooth? Well, for these super high-performance parts in aerospace or medicine, the surface finish isn't just about looking good. It can literally be a matter of life and death. A perfect surface means the part works exactly how it's supposed to and for as long as it's supposed to. Any little flaw, no matter how tiny, can become the starting point for a total, catastrophic failure down the line.
And here's the central problem, the real kicker of this whole process. The cutting tool, the thing that's carving out this perfect shape, is actively wearing itself out with every single pass. It's in a constant state of self-destruction, and every little bit of decay from that tool gets directly transferred to the very surface it's trying to make perfect. It's a paradox.
Okay, so to really understand the problem, we've got to start at the source. We're not talking about a tool just snapping in half. No, it's more like a slow creeping death, a bunch of different ways the tool wears down that together act like the very first domino to fall.
And listen, it's not as simple as the tool just getting dull. It's way more complex. You've got flank wear, which is basically friction just rubbing the side of the tool away. Then there's crater wear, where super hot metal chips literally gouge a crater out of the tool's face. You've also got chipping, which is just what it sounds like, tiny little fractures that break off the sharp cutting edge. And finally, notch wear, which focuses all that stress and damage right at the cutting line. Each one is like a different enemy attacking the tool.
And this isn't just some textbook theory, right? When researchers looked at super tough materials like Inconel, the stuff used in jet engines, they saw this connection plain as day. A recent study from 2023 confirmed it. As the tool wears down, the surface gets rougher and you get more burrs, and those awful little slivers of metal that hang off the edge. The takeaway here is simple. A dying tool makes a bad part.
But that first bit of tool wear, that's just the beginning. It's the spark that ignites a massive chain reaction, a whole cascade of problems, where one tiny issue quickly spirals into a bunch of bigger ones.
So here's how those dominoes tumble. First, the tool edge gets dull. Now, because it's dull, you have to push harder, which creates way more friction and heat. All that extra force and heat means the tool isn't cutting cleanly anymore, it's just plowing and tearing through the material. And here's the really critical part. The damage is no longer just on the surface, it starts getting shoved down into the material itself.
And we see this everywhere. Just this past year, a study on tough stainless steels, the kind you use for parts that are under a ton of stress, saw the exact same thing. As the tool wore out, it started plowing material instead of cutting it, completely wrecking the finish. It's a universal problem in manufacturing.
So, up to this point, we've been talking about problems you can actually see and feel, like a rough surface. But the most dangerous part of this whole story is what you can't see. It's the damage that's happening just below the surface.
And this is where it gets really scary. All that heat and force from the worn tool, it creates tiny micro cracks that are like little ticking time bombs waiting to grow. It can also form something called white layers, a super hard but really brittle layer that can just flake off. It locks in stresses that are constantly fighting the material's own strength, making it weaker. You're basically changing the metal's DNA, and not in a good way. And we know exactly how this happens. Research on a key aerospace titanium alloy, T6Al4V, connected all the dots. As the tool wears down, the temperature skyrockets. That heat directly causes more deformation and more cracks to form just under the surface. It is a perfect storm for failure.
And hey, don't just take my word for it. As one research team put it back in 2022, all this hidden damage, the stresses, the tiny cracks, it all leads directly to a part that gets tired faster and doesn't last as long. In other words, the part is going to break way sooner than it should, all because the tool that made it was wearing out.
So yeah, that all sounds pretty bleak, right? But this is a battle, and engineers have come up with a really incredible toolkit of advanced tricks to fight back and break this chain reaction of damage.
One of the coolest, literally, weapons in the arsenal is extreme cold. It's called cryogenic machining. You basically blast the cutting area with liquid nitrogen to keep everything incredibly cold, which directly attacks the main villain of our story, heat.
And the results? They are just night and day. Just look at the difference for that titanium alloy. Compared to cutting it dry, Flooding it with liquid nitrogen massively reduces heat damage, the tool wears down way slower, the surface finish is way better, and you get far fewer of those dangerous hidden defects. It's an absolute game changer.
Another really smart technique is MQL, which stands for Minimum Quantity Lubrication. Instead of drowning the part in coolant, MQL uses this superfine, targeted mist of oil and air shot right at the cutting edge. Think of it like a sniper rifle versus a fire hose. It's a precision strike against friction, and it barely uses any fluid.
Okay, now get ready for a total mind bender. What if, instead of fighting heat with cold, we fought it with more heat? It sounds crazy, I know, but that's the whole idea behind thermal-assisted machining. You use a laser to heat up the metal right before the tool gets there, which makes it softer. And a softer material is easier to cut, meaning less force, less friction, and less tool wear.
So just how well does that crazy idea work? Well, let me just throw one number out there for you, 91%. What does that mean? It means a recent study found that using this preheating method on a tough tool steel made the surface an incredible 91% smoother. By making the material just a little bit softer, they practically eliminated all that plowing and tearing we were talking about earlier.
Now, these techniques are amazing, don't get me wrong, but they're all about playing defense, preventing problems from happening. The next giant leap in this field isn't about prevention. It's about seeing problems as they happen and reacting in real time. And this is where we start getting into stuff that sounds like science fiction. Researchers are actually building systems that give machines senses, the ability to measure the surface roughness and check on the tool's health while it's cutting. I mean, imagine a machine that can actually feel its own tool wearing down and see the microscopic damage it's causing, all in the moment.
And that really leads us to the final big question. If a machine can see a problem happening in real time, could it one day just adapt? Could it adjust how it's cutting to make up for the wear? Or maybe even trigger a little robot to come in and sharpen or replace its own tool, long before any real damage is done? The battle for the perfect surface is still raging on, and it looks like the next generation of soldiers might just be intelligent machines themselves.